structure of atom.
Hello friends, I am an atom. Yes, an atom. Can you see me? Oh yes, I know, you can see me on your screen. But I'm just an imaginary picture of an atom. Real atoms are too tiny. Now, I have a question for you. Do you know the structure of mine? Am I divisible? Let us see.
Ideas about the atomic structure. In the early days itself, there was some understanding in the idea of construction of matter. An Indian philosopher, Maharishi Kanad, postulated that everything in the universe is created with the smallest particle, which cannot divide further. Around the same era, ancient Greek philosophers, Leucippus and Democritus told that the universe is created by small particle, namely atom. But another Greek philosophers, Plato and Aristotle, does not accept these ideas. Their argument is that the universe is created by the four elements called earth, air, water, and fire. Similar to this, there was a belief in ancient India that the universe is created by the five ghosts, such as air, water, earth, sky, and fire. A scientist lived in Rome, Lucretius, proposed an idea that the matter is created with particles which cannot divide further. All these were based on philosophical considerations and not much experimental work to validate these ideas. By the end of 18th century, scientists recognized some points about the mass and indivisibility of particles when they were experimenting to find what happens when elements combine. Two things were evolved in these experiments, are called the law of conservation of mass and the law of definite proportion. In 1774, the French scientist Antoine Lavoisier found that the mass can neither be created nor destroyed after a chemical reaction. This experiment will help you to understand this. Take calcium chloride solution in a conical flask. A test tube containing sodium sulfate solution is inserted into the conical flask, as shown. Find the total mass of solution with the apparatus. This is showing 369 gram. Turn the conical flask upside down so that all the solution in the test tube should mix the calcium chloride solution and mix well. We can see that a chemical reaction is happened, and so a white precipitate of calcium sulfate is produced. Again, find the total mass when the reaction stops. Still it is seen that the total mass is 369 gram. The mass is same before and after the chemical reaction, isn't it? From this experiment, we can understand that mass can neither be created nor destroyed in a chemical reaction. This is known as law of conservation of mass. Law of constant proportions. Everybody knows what is compound, and it is also known that the mass of elements in the compound has a definite proportion. But in 1799, a scientist named Joseph Proust stated that in a chemical substance, the elements are always present in definite proportions by mass. This is known as law of definite proportion. Look at this oxygen atom. Nothing is happening when a hydrogen atom comes near. But, if another hydrogen atom comes near, as you know, water is a compound. And, we know all the sources of water. And we can prove that the ratio of mass of hydrogen to the mass of oxygen in the water is always 1:8, whatever the sources of water, or where it comes from. From this relation only, molecular formula of water, H2O, is confirmed. Let us find the ratio of masses in some more compounds. In carbon monoxide, the ratio of mass of carbon to oxygen is 12:16. That is 3:4. In methane, the ratio of mass of carbon to hydrogen is 12:4. That is 3:1. In sulfur dioxide, the ratio of mass of sulfur to oxygen is 32:32. Thus 1:1. Have you understood that, in a chemical substance, or compound, the elements are always present, in definite proportions, by mass? In 1807, British chemist John Dlaton provided the basic theory about the nature of matter. By taking the name atoms, as given by the Greeks, he said that all matter, whether an element, a compound, or mixture, is composed of small particles, called atoms. He postulates the atom theory as follows. All matter is made of very tiny particles, called atoms. Atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. Atoms of given element are identical in mass and chemical properties. Atoms of different elements have different masses and chemical properties. Atoms combine in the ratio of small whole numbers to form compounds. The relative number and kinds of atoms are constant in a given compound. Charged particles in matter. It was thought that no charge was in the matter formed by atoms. But it is understood that matters are getting charged under certain circumstances. Let us see an example. Comb a few times with a plastic comb to the dry and non-oily hair. Then show this comb to the tiny little pieces of paper on a tabletop. You can see that the pieces of paper are getting attracted to the plastic comb. The reason could be that electrically charged particle should be present in the matter, isn't it? By the end of 19th century, English scientists Humphrey Davy and Michel Faraday did some experiment by conducting electricity into the solutions. They are given clear indications about the presence of charged particle in the matter. So, there was a strong thought developed that there could be smaller charged particles in the atom. And it was also proved on the later experiments. Let us see, in the next section, how the unknown charged particles found. Formation of the structure of atom. In 1886, a German scientist named Mr. Goldstein, who was engaging experiments on discharge tubes, forecast the presence of charged particle in the matter. But, in 1897, an English scientist, Mr. J. Thomson, found the negatively charged particles in the atom. He designed a glass tube, filled with low-pressure gas, and containing two metal plates inside. When he put a big electric charge on the plates, he found that the positively charged plate, called the anode, was able to pull a beam of tiny particles out of the negatively charged plate, called the cathode. Because the beam came from the cathode, He called them cathode ray. And he called the apparatus a cathode ray tube. When the cathode rays arrived at the anode, there was a little hole that allowed them to travel through and continue to pass between a pair of parallel plates that he could put varying charges on. Sometimes the top one was positive with the bottom one negative, and sometimes the other way around. The beam always bent away from whichever plate was negative, and towards whichever plate was positive. This meant that the particles must have carried a negative charge, because we know that like charges repel and unlike charges attract. But here is the thing. Because the beam bends so easily, the particles going through the plates, he could work out that they must have been very light, thousands of times lighter than a hydrogen atom. Thomson realized that atoms had even smaller particles inside them, and that they carried a negative charge. Thus he has discovered electron. He won the Nobel Prize for this. Electron has a mass of 1 by 1837 of mass of hydrogen. Thomson introduced about the structure of atom after he realized the presence of positive charged particles and negatively charged particles. He proposed the model of an atom to be similar to that of a Christmas pudding. The electrons in a sphere of positive charge were like dry fruits in a spherical Christmas pudding. The number of positive charge particles and the number of negatively charged particles in the sphere are equal, and so electrically neutral, Thomson said. The model of atom by J. Thomson helped the experimentation of electron distribution in an atom in later days. Rutherford's atom structure. In 1909, a scientist named Ernest Rutherford, who started the study about the electron distribution in an atom. In 1911, he conducted the gold foil experiment by making positively charged alpha particles fall on a thin gold foil. This helped to give clarity to the structure of atom. In this experiment, a radioactive source of alpha particle was placed in a lead box containing a small hole. The alpha particle, which hit the inside of the box, was simply stopped by the side wall of box. Only those alpha particles which passed through the opening were allowed to escape, and they were confined to a straight line. They passed through the lead sheet with a small slit. They are bombarded to the extremely thin gold foil. The alpha particles which were scattered were detected using a detector and a circular fluorescent screen which was coated with zinc sulfide. As such, Rutherford observed that most of the alpha particles passed straight through the foil, which implies that most of the space inside the atom is empty. Some alpha particles were deflected by the foil at small angles, indicating the interactions with other positively charged regions within the nucleus. Very few alpha particles bounced back to the source, indicating that all the positive charge was concentrated in a small volume within the atom. He called this place as nucleus. The positively charged particle in the nucleus are protons. It was found that the proton have nearly equal mass of hydrogen atom. Based on these observations, Rutherford put forward the nuclear model of an atom, which has the following features. There exists a positively charged center in an atom called the nucleus. The size of the nucleus is very small as compared to the size of atom. Nearly all the positively charged particles and most of the mass are concentrated in the nucleus of atoms. Negatively charged electrons revolve around the nucleus in circular paths. Rutherford's atom model is known as planetary model of atom. Limitations of Rutherford's atom model. But some of the observations in later years found limitations in the Rutherford's atom model. according to the electromagnetic theory put forward by the Scottish scientist James Clerk Maxwell. A charged body in circular motion continuously emits energy as radiations. Electrons, which revolve around the nucleus, should emit electromagnetic radiations, lose energy, and come closer to the nucleus. Finally, the negatively charged electrons should collapse into the nucleus. But this does not happen in an atom. Rutherford's model failed to explain this. Bohr model of atom. The Danish scientist Niels Bohr put forward an atom model by resolving the limitations of Rutherford's atom model. His ideas are like these. Electrons revolve around the nucleus in fixed paths, are called orbits or shells. Electrons in each shell have definite energy. Hence shells are also called energy levels. As long as an electron revolves in a particular orbit, its energy remains constant. The energy of the shells increases as the distance from the nucleus increases. The shells around the nucleus can be represented from near the nucleus by the letters K, L, M, N, etc. In 1920, Rutherford predicted that nucleus may contain neutral particles having mass equal to that of protons. The actual mass of an atom should be equal to the sum of the mass of particles present in it. Based on this, the total mass of helium atom is measured. When the masses of electrons and protons in the helium atom are calculated, it was found that the value obtained was 1/2 that of the actual mass. Scientists realized the fact that there is no relation between the total mass of particle, that is, electrons and protons in an atom, and the actual mass of the atom. What can be inferred from this? It may have contained a new particle other than proton and electron, isn't it? In 1932, an English physicist named James Chadwick discovered a beam of new particles with about the same mass as protons. He did this by shooting alpha particles into beryllium atoms and knocking these particles out of the beryllium nuclei. The beryllium target was much thicker than Rutherford's gold foil, so there were many more nuclei for the alpha particles to make direct hits with the beryllium nuclei, which has an atomic number of 4. So, he knew that they had 4 protons each. But he was experimenting to find new particles in the nucleus. When these particles were struck by the alpha particle bullets, they were knocked out of the nucleus, and then continued in a beam Chadwick could study. This beam did not bend when passed through charged plates, like the electrons of Thomson's experiment did. This meant the newly discovered particles had no charge. Because these particles were electrically neutral, he named them neutrons. The mass of neutrons determined is slightly higher than that of proton. Mass numbers and atomic numbers. It is discovered that an atom contains particles like electrons, protons and neutrons. These are 3 particles, are known as the fundamental particles of an atom. Let us compare and study the mass and properties of the fundamental particles. The mass of a microscopic particle like electrons, protons and neutrons were in fact very small. The mass found in the fundamental particles are shown. The mass of proton is 1.6726 into 10 raised to minus 27 kg. The mass of electron is 9.109 into 10 raised to minus 31 kg. And the mass of neutron is 1.6749 into 10 raised to minus 27 kg. The unit of the above particles are known as atomic mass unit, U. As a result of the recent advancement in scientific techniques, several methods are now available to determine the accurate masses of atoms. Earlier, the relative atomic mass method was used. In this method, the mass of any atom is expressed by comparing it with the mass of a particular atom. For this purpose, the hydrogen atom, being the smallest in size and possessing the least mass, was taken as a unit. The masses of other atoms were stated by comparing them with that of hydrogen. But due to certain scientific reasons, 1/12th mass of a carbon-12 atom is now accepted as the atomic mass unit, U. This is calculated as 1.6605 into 10 raised to minus 27 kg. If we tell the masses of fundamental particles in terms of atomic mass unit, then the mass of proton is 1.00727 U. Mass of electron is 0.005484 U, and the mass of neutron is 1.0086664 U. In short, for practical purposes, the mass of proton and neutron would be 1 atomic mass unit, and the mass of electron, 0 atomic mass unit. That means, mass of atom depends upon the mass of proton and neutron. So when we calculate the mass of an atom, the mass of electrons are not considered. For example, an atom having 1 proton and 1 neutron has mass of 2 atomic mass unit. An atom having 2 protons and 2 neutrons have a mass of 4 atomic units. And that of 4 protons and 5 neutrons have a mass of 9 atomic mass units. To identify an atom clearly, the mass number is written on the upper side, and atomic number on the lower side, of the letter representing an element. The mass number has a symbol A. The total number of protons and neutrons in an atom is nothing but the mass of an atom, and it is called the mass number. This mass number, A, tells you how many protons and neutrons were in one atom of an element. We need to remember that protons and neutrons each have a relative mass of 1 unit, and those electrons are so small that their mass does not need to be considered in the mass number of an atom. That is, mass number A equals number of protons plus number of neutrons. The atomic number has the symbol Z. This number tells you how many protons are in one atom of an element. The number is always the same for atoms of a particular element. Atoms of different elements have different atomic numbers, meaning they have different numbers of proton. For example, an atom of hydrogen has an atomic number of 1 because it has 1 proton. But an atom of oxygen has an atomic number of 8 because it has 8 protons. So, if we know the atomic number of an element, we can find the number of protons and electrons in an atom. Atomic number equals number of protons equals number of electrons. If we know the mass number and atomic number of an element, we can calculate the number of neutrons in an atom of particular element. So the mass number equals the atomic number plus the number of neutrons. The atomic number is just the number of protons in an atom. Therefore, the mass number equals the protons plus the neutrons. So if we take oxygen, oxygen has a mass number of 16, and an atomic mass of 8, how many neutrons does it have? Remember, mass number equals the number of protons plus the number of neutrons. The number of neutrons equals mass number minus the number of protons. Equal to 16 minus 8 equals 8. Oxygen therefore has 8 neutrons. Let us take another element, lithium. Lithium has a mass of 7, and an atomic mass of 3. How many neutrons does it have? Number of neutrons equals mass number minus the number of protons. Equals 7 minus 3 equals 4. Lithium, therefore, has 4 neutrons. In short, the atomic number is the number of protons in an atom, and the mass number is the number of protons and neutrons in an atom. As you have studied earlier, electrons revolve around the nucleus in well-defined orbits. And you have understood these shells, or energy levels, are represented by the letters K, L, M, N, etc. Now, let us know, what is the electron arrangement in the shells? The filling up of electrons in shell is based on the following principles. 1. The maximum number of electrons that can be accommodated in any given shell is 2n square. N is the shell number. 2. Shells with lower energy will be filled with the maximum number of electrons first. Thereafter shells having higher energy get filled. 3. The maximum number of electrons that can be contained in the outermost shell of an atom is 8. Bohr model of atoms of certain elements are showing. Helium, lithium, beryllium, carbon, neon, sodium, isotopes. As you know, the number of protons and neutrons in the atom of an element decides which is that element. And the number of protons and neutrons is always same in an element. But, in some of the elements, the number of neutrons may vary. That is, if some of the elements have same number of protons and different number of neutrons, then we call that element as isotopes. We are going to use hydrogen as our example. Hydrogen has 3 major isotopes. The most common isotope of hydrogen has 1 proton and 0 neutrons. Then the mass of this atom would be about 1 atomic mass unit, just the mass of proton. This isotope of hydrogen has a special name, protium. We can see another hydrogen atom. Its nucleus contain 1 proton and 1 neutron, so it has a mass of about 2 atomic mass unit. This isotope of hydrogen is known deuterium. The last isotope is called tritium. It has, as you may guess, still only 1 proton, but it contains 2 neutrons in the nucleus, giving a mass of 3 atomic mass unit. What do you understand from this? There are 3 isotopes for hydrogen, which has different mass number. That is, protium, deuterium, and tritium are the 3 isotopes of hydrogen. The isotopes of carbon atoms are known as carbon-12, carbon-13, and carbon-14. Isotopes are of great importance in diverse fields. Deuterium, the isotope of hydrogen, is used in atomic reactors. An isotope of carbon, carbon-14, is used to determine the age of fossils and prehistoric objects.